Well, hello everyone, and welcome to today's lecture on memory with Verilog. In this lecture, it's going to be a bit more theoretical on the different kinds of memory, but there will be some Verilog code near the end. Alright, so memory in digital systems. Memory is an electronic device or subsystem used to store binary information such as bits, zeros, and ones. It provides storage, retrieval, and sometimes modification of data in digital systems such as microcontrollers, processors, or FPGAs. At a high level, memory systems are defined by capacity, the total number of bits or bytes stored, access method, how data is retrieved or written, speed, how fast data can be read or written, and volatility, whether data persists after the memory is powered off. So, architecture and terminology. So, a byte is the smallest unit of information. A bit. A byte is 8 bits. It's a standard addressable unit in most systems. A word is a group of units processed as a single unit. So it is usually 16 or 32, just depending on the kind of system you're using. An address is a binary number identifying a unique memory location. A memory cell, a circuit capable of storing 1 bit of data. And an array, the organized collection of memory cells. Access time, the time between read-write requests when data is available, and cycle time, minimum time between successive memory operations. In Verilog and hardware design, you often model memory as an array of registers. Example, Reg 7 to 0 or Mem 0 to 255. The memory model. A memory map is a conceptual representation that shows how memory addresses correspond to a physical or logical components. It defines which address ranges are assigned to. Program memory, or ROM, data memory, like RAM, I/O devices, and special registers. For example, you can see this example memory map. So in this area, you might see some program ROM. In this area, you might see some data RAM. Here are some I/O registers, and here might be some EEPROM, and then finally some reserved or unused areas. The CPU's address lines determine which device responds to a given address. This mapping can be fixed or inconfigurable. Volatile versus non-volatile memory. Volatile memory loses stored data when power is turned off, fast and widely used for temporary storage. Examples include SRAM, DRAM, and register files. Non-volatile memory retains data when power is off, used for permanent storage of programs, firmware, and configuration. Examples, ROM, flash memory, and EEPROM. Read-only memory versus read-write memory. Read-only memory. Data can only be read, not written, during normal operation, typically programmed once during manufacture or via special process, used for permanent instructions or lookup tables. So here's the different types of ROMs. So mask ROM is factory programmed, is not erasable, and is hardwired. PROM, or programmable read-only memory, is programmable once, not erasable, and it consists of programmable fuses. Electrically programmable read-only memory is programmable, is erasable via UV light, and has an erasable chip. And then EEPROM is programmable, is electrically erasable, and uses flash or EEPROM cells. Flash memory is a special EEPROM variant allowing block erasures and rewrites. Read-write memory, or RAM, always allows both read and write operations dynamically, used for temporary data storage and runtime variables. So for static RAM, refresh is not needed. It is used commonly in CPU caches and small buffers. DRAM or dynamic RAM needs to be refreshed and is usually used in main memory. And then SDRAM or DDR is the refresh is needed and is a high-speed system memory. Random access versus sequential access. Random access memory, any location can be accessed directly or quickly using its address. Access time is independent of address location. To access the address 0, It is equal to the time to access address FFFF. Sequential access memory. Data must be accessed in a predetermined order. Access time depends on data position. Example, magnetic tapes, shift registers, or FIFO buffers. To access byte 100, you need to first read bytes 0 to 99 sequentially. Non-volatile memory. Non-volatile memory stores data using physical mechanisms that maintain so non-volatile memory stores data using physical mechanisms that maintain state without power, such as fuses or antifuses, charge stored in a floating gate transistor, magnetic or fuse change elements. Non-volatile memory is used for firmware, configuration storage, bootloaders, and long-term data retention. Although internal structures vary by technology, most NVM devices share. So, the component. Memory cell array stores bits in rows and columns. An address decoder selects which word or byte to read or write. SIMPS amplifiers to detect low current changes to determine the stored bit value. Control logic manages programming, erasing, and timing. I/O interface provides external access to data. ROM, or read-only memory. ROM is permanently programmed during fabrication and cannot be modified later. It is used in simple consumer electronics, calculators, and fixed boot code. Architecture. Memory is formed from a fixed array of logic connections, and it stores a hardwired pattern of zeros and ones. It is not programmable nor erasable. It has very high reliability and used as permanent firmware in mass-produced products. Mass ROM. Mass ROM is the original form of ROM and is programmed by altering a metal mask layer during chip fabrication. It is best used for high-volume devices due to low per-unit costs. Also, it is not flexible. Any bug requires a new mask. The data pattern is defined by a photolithography mask. A 1 or 0 is created by adding or omitting a connection at each cell. It can be programmed at the factory. Cost per unit is low, and lead time is long. Use in game cartridges and a fixed BIOS. A programmable ROM. A programmable ROM can be programmed once by the user and is typically using a PROM programmer. An architecture uses fuse or anti-fuse technology. Programming blows a fuse to record a permanent bit. It is not programmable, uses fuses, and is used as a device configuration or permanent calibration data. Erasable programmable ROM. An erasably programmable ROM can be erased and reprogrammed, but erasure requires an ultraviolet light. You must erase the entire chip before reprogramming. It was historically used for firmware development. It uses floating gate MOS transistors. Programming stores charge on the floating gate to represent 1. A UV light erases by removing charge from all cells at once. Chip has a quartz window exposing silicon to UV light. Reprogrammable. Erase method, UV light. Erase time is 20 to 30 minutes and is used for development or prototyping prior to an EEPROM existence. Electrically erasable programmable read-only memory. EEPROM improved on EEPROM by allowing electrical erase and rewrite, enabling selective erasure at bit or small block level. It is more flexible than EEPROM. EEPROM also has slower write or erase cycles than Flash. It still uses floating gate MOS transistors, electric field tunnels, or electrons onto or off the floating gate, and allows in-circuit programming. It is reprogrammable, has an electrical selective byte erase, is random access, and is used in BIOSes, configuration memory, and in smart cards. Flash memory. Flash memory is a type of EEPROM optimized for fast block-based erase and rewrite, making it suitable for mass storage. It uses floating gate transistors like EEPROM, and cells are grouped into blocks/sectors. Arrays operates on entire blocks rather than individual bytes. There are two main types: NOR flash, which is random access and used for code detection, and NAND flash, high density and used for storage. So NOR flash is random, but NAND is sequential. The density is lower, but in NAND is higher. The cost is higher in NOR, but it's lower in NAND. And they use NOR is used for firmware and boot, and NAND is used for mainly just storage. Volatile memory. Volatile memory requires continuous power to retain data. It is primarily used for high-speed temporary storage during system operation. The two major types are SRAM and DRAM, each with distinct architectures, performance, and cost trade-offs. Data is stored using electronics, charges, or states that disappear when the power is removed. Used as working memory for processors due to speed. Key performance goals: fast access, high density, low power, and low cost. So SRAM, or static random access memory. SRAM stores each bit using a bistable flip-flop circuit made of 4 to 6 transistors. Typically it includes 2 cross-coupled inverters to store the state 0 or 1, and 2 access transistors to control the read-write access to the cell via bus lines. SRAM is used in CPU caches, small fast memories, and low-power embedded systems needing fast access. It is the fastest RAM, but it is too expensive to be the large main memory. Data storage: a flip-flop holds the value as long as it is powered. A refresh is not required. It is very fast. It is a low density, high cost, and a higher static power consumption. Dynamic random access memory. DRAM stores data as a charge on a capacitor with a single transistor controlling access. A capacitor holds charge, and an access transistor connects the capacitor to a bit line when the word line is active. The charge leaks over time, so the memory must be periodically refreshed. A DRAM controller automatically performs refresh cycles. SRAM is used in main system memory, graphics memory, and mobile memory. SRAM is higher density and lower cost, but it needs to be refreshed and is slower. Alright, so here's an example of ROM in a small, simple asynchronous read in Verilog. So we declared a parameter called address width equal to 4, input wire of address, and an output register of data. So we begin in an always loop. For any address, we write into data these values 0, 1, 2, 3, 5, 6, 7, 88, and 89, and the default will be FF. This is good for small lookup tables where address decoding is explicit. Notes: asynchronous combinational read, output updates whenever address changes. For larger tables, this becomes unwieldy. Memory array ROM for file initialization. So we declare an address width and a data width parameter, an input wire and an output wire called address and data. We declare our memory depth, so address width will be shifted by 1. And then ROM storage, this is synthesizable. So we declare a register data width -1 to 0 and a mem 0 to depth 1 -1. Alright, asynchronous read output, we combinational read and initialize from file at simulation start. So we read from ROM contents.hex into memory. Okay, and this is a synchronous ROM or registered output. And so, similar to before, we declare an address width and a data width, a clock, an address, and a data queue. We define our depth of our address width shifted by 1, and then we declare a mem array, and then we initialize. So we read the contents of ROM contents.hex into mem, and then we read from mem at the index address into data queue at every clock cycle. Alright, here's a test bench to just test the code from before. So we declare an address, a data async, a clock, and a data synchronous. So we read memory, so we use the ROM read MH module from before. We also use the ROM synchronous module from before. Then we initiate our clock, and then we swap addresses, and we just display the contents of the ROM. A simple single port RAM, asynchronous read or synchronous write. So we declare our parameters address width and data width. We declare a clock, a write table, an address, a data in, and a data out. Address width gets shifted by 1. And we declare register memory with, that's a double array. Okay, and then if write is enabled at every clock cycle, data in is set equal to the address index of mem, and then data out will be equal to the index address of mem. Asynchronous read write RAM. Alright, so same as before, we declare a clock, write enable, address, data in, and data out. We declare a depth, our memory, and then at every clock cycle, data in will be read into memory, and then data out will be equal to the memory contents. Alright, then a dual port random access memory, one read and one write port. So we declare our clock, our write enable, our write address, our data in, our read address and data out, our depth, our memory, and for every clock cycle, the data in is assigned to the write address of memory, and data out is assigned the read address of memory. Alright, and then the test bench. So we declare some variables, write enable, address, data in, data out. We initialize the RAM synchronous method, calling it device under test, and then we set our variables equal to 0. We write, and we read back, and then we just monitor for any changes. Alright, so that concludes this lecture. Thank you very much for watching.